In today's presentation, I will provide some highlights of accelerated bridge construction in high seismic zones and the peculiarities that we have to be concerned. Why high seismic zones matter? The reason for that is that ABC relies heavily on precast members that are connected in the field. Therefore, connections become of critical consideration. Here we're looking at a two-column bent being pushed by seismic forces. You would note that these precast members, namely the cap beam, the columns, and in many cases footings, they have to be connected right. In one instant, when the seismic forces go from, let's say, left to right, we see that these connections at the top of columns are subjected to opening on the right side and closing on the left side. Once the earthquake force is reversed, the same connection you notice now is subjected to opening on the left side and the right side. During a seismic event, this process gets repeated over and over. It is therefore important for these connections to maintain structural integrity under seismic loads. What are the seismic performance requirements for bridges anyway, regardless of being cast in place or precast? For cast in place conventional construction, the requirements are no collapse under strong earthquakes, plastic hinging of the columns are expected to form structural fuses. Other than the columns, the cap beam and the footing, they are designed to remain elastic, or they are capacity protected. No damage should occur in these elements. When it comes to ABC connections, when we are using precast members, the bridge functions or expectation is still the same as cast in place conventional construction, meaning that we should not have any collapse. We should expect plastic hinging in the columns, and the cap beams and footings should be capacity. In both conventional and ABC type of bridges, when we use concrete and steel, the expected damage in columns would be the same, meaning that in both cases we have to develop plastic hinges at the end of the columns and expect to have severe damage at the end of the columns because they would act as structural fuses. A valid question that is raised when we are using ABC is this. Now that we are manufacturing these columns in a plant where quality control and precision is at a higher level than field construction, can we switch to other types of materials that would prevent damage? We still have a safe bridge with respect to resisting strong earthquakes, but we could potentially reduce reduce the damage at plastic hinges? This is a very valid question, and in my opinion, the answer is yes. Although it is something that would have to be covered in another presentation. Let me go back to different types of connections. We might place these connections into three different categories. One would use couplers, another group would use no couplers at all, and there are other types that would not necessarily fit into the other two categories. I'm going to briefly discuss these connections. Let's start with couplers, also known as mechanical bar splices. Couplers have been used for a long time for non-seismic applications. Here are two examples. One is a grouted sleeve coupler that is used in superstructure of a bridge, connecting bars coming from one segment to the other. Another type that's shown over here is the so-called headed bar couplers, where the bars that are to be connected are equipped with heads with a flattened end, and there are couplers that are placed on the bar before flattening the end, and then these couplers get connected from one side to the next. The problem with couplers is that in current bridge seismic codes, they are not permitted in plastic hinges of bridges that are in moderate and high seismic areas. AASHTO, Caltrans, neither code allows for these couplers for a variety of reasons that we do not have time to get into. The American Concrete Institute, ACI, does allow couplers in plastic hinges under certain conditions, but that's applicable to buildings, not bridges. Despite the ban, there have been some studies on these couplers in bridge columns under seismic loading. Recent studies of grouted couplers in Nevada, Utah, and Florida have shown that we can accomplish a displacement ductility of 4.4, 4.5, or more. For many seismic applications, that might be sufficient. The study at the University of Nevada, Reno on columns with headed bar couplers has shown that we are able to accomplish a displacement ductility of 7, and the column performance was the same as that of a conventional cast-in-place construction, meaning essentially no change in the behavior, no compromise in ductility. With grouted couplers, there was some reduction in ductility when we use these couplers. These data put into question that should we continue to ban couplers in plastic hinges? And there are people who are trying to answer that, including some of the work that I am doing. Let's talk about the second category that I mentioned, and that is non-coupler options. There are different choices here. We could use grouted ducts, we could use pre-stressed systems, pocket connections. There are also embedded columns. The advantage of this group of connections is that they do not violate the band that exists in current AASHTO and Caltrans codes. The grouted ducts are connections that can be used for column to cap beam or column to footing connections. An example of column to cap beam connection is shown over here. In this slide, you see the grouted the ducts that are to be filled with grout later are placed into a footing. This is before all the reinforcement are placed in the footing. And in this slide, you notice that there's a precast column. This is the lower end of the precast column, and these are the dowels that are protruded from the precast column and are being inserted into these ducts that are filled with some grout. A case of a pre-stressed system. One case is shown over here where the entire column is precast and it's pre-tensioned. Another case is shown over here where the columns are built in segments and the entire column is post-tensioned. This is an entire pier that has been precast, assembled, and is being placed on a shake table at the University of Nevada, Reno. Pocket connections. Here you see an example of pocket connections for cap beams. On the left, you see a column with the protruded reinforcing bar from the column that are inserted into a pocket that is left in the precast cap beam. The space is then filled with concrete. Another example, the column is fully precast and is inserted into a pocket. In this case, we use grout to fill the space between the column and the pocket. The example that you see down here is of that same nature. There is a fully precast column. In this case, it's a composite column that is being lowered onto a pocket that is left into a footing. Then the space is filled with grout afterward. Embedded columns are columns that are precast but are placed into a cast-in-place footing. So here you see the footing before the placement of all the reinforcement and concrete. Another option here is the concrete-filled steel tube that is again precast. It is placed into a footing. Then the footing is cast in place. There have been studies on non-coupler options, and we have found that we are able to accomplish excellent performance. And what is meant by excellent is we are able to match the overall performance that we would see in a conventional cast-in-place column. The question is, of these options within the non-coupler cases, which one would we want to use? There is some evidence that engineers are moving towards using grouted ducts. This is because this detail is the closest detail to conventional reinforced concrete construction. By basically anchoring the bars in these grouted ducts, no other design considerations exist. Let's talk about other options. In one option, you have pins or hinges that could facilitate construction. We also have a new emerging type that has been studied only recently that deals with replaceable plastic hinge elements with detachable connections. Examples of pins and hinges are shown over here. So here we are looking at a two-way rebar hinge. In this case, the precast column, which is hollow, can be placed on top of the rebars, and the space is later on filled with self-consolidating concrete. Another example is pipe pin. These steel pipe pins have been used in practice for cast-in-place construction. Studies at UNR have shown that yes, we could take these and use them for precast construction for ABC as well. An example of that is shown over here, where you have a precast cap beam being lowered onto pipe pins that are embedded in the precast columns that you see over here. Now, that brings me to an interesting question about a terminology that we hear often from engineers and researchers. Can we make ABC emulative of cast-in-place construction? Which one of these details or connections give us that? Well, the answer is we could make it emulative depending on the particular seismic or maintenance parameter we are looking at. When it comes to seismic performance, it is possible to make the seismic performance of ABC columns match the performance of cast-in-place construction, depending on the type of connection that we use. The design of ABC could be close to what we have for CIP, however, could be drastically different. For example, if you're using grouted ducts, the design can be similar to cast-in-place construction. If you're using longer couplers, there may be significant deviations from conventional design because of the effect of couplers on plastic hinging. The construction is definitely non-emulative because it's very different than what we use in cast-in-place construction. Tolerances are also very different. In having precast segments, we have to make sure that these precast segments fit and the connections come together in the field. That requires relatively tight tolerances. When it comes to maintenance, emulative is not necessarily, the ABC is not necessarily emulative because the places where we use grouts, there is concern about the quality of grouts. And perhaps until we build a history of field performance of these grouts and ABC column connections, we need to visit, we need to inspect, and perhaps spend more time on maintenance of these grouts. Inspectability, generally, ABC is emulative. We should not have any issues inspecting ABC members, except for the columns where we use unbonded post-tensioning. Unbonded post-tensioning would require extra attention because of the susceptibility of unbonded steel tendons to corrosion, unless we switch to fiber reinforced polymer tendons. Again, that's a subject of another presentation. Finally, when it comes to repair, we could think of ABC as being something that is emulative as cast-in-place conventional construction, assuming that the connections are designed and constructed properly and there are no flaws in either design or construction. I hope from today's presentation you were informed about some general aspects of ABC.